Okay, so I apologize for the way that this video is coming out, but I am trying to make this as good as possible. I accidentally left the field notes at home, so I'm going to do a walkthrough based on the online field notes. Hopefully you can follow along with this little hand cursor here, but I will try to make sure I explain everything that I've written down in the field notes. So today our goal is to write the equation of 3 different vectors, and these vectors become important as we define different planes when we deal with space curves. And it also becomes important to talk about their relationship between each other. So we have already been over the unit tangent vector. This was a review from a prior lesson. Hopefully you will know this for the 12.1 through 12.3 quiz. So the unit tangent vector, big T, is equal to r prime of t over the magnitude of r prime of t. So in this first example, we're just reviewing on how to find that. We're just practicing. So the first thing I need to do is take the derivative of r prime of t, which I've done here, using this specific function, r of t. And notice that in this problem, I want the unit tangent vector at a specific time, t equals 2. So instead of finding a generic formula for t of t, I'm going to go ahead and plug in 2 into this function so that I can find a specific vector. And once I found that specific vector, I'm going to divide to find that specific vector's magnitude, which is way easier than finding a formula for the magnitude. So I've plugged that in. I have simplified a little bit here. I've only simplified because there is a factor of 16 in here, which comes out as a nice factor of 4, which is every single one of our elements or our components of r prime of 2 is divisible by 4. So I've done a nice simplification here. That's not required, but if you have a calculator on your test, and maybe if you need to use this vector for something else, you would like to make it as simple as possible so that when you use it going forward, you don't have to do the difficult math that might be required if it looks like this, or with this square root of 1184. Notice one other thing here. This is t of 2, not t at any time t. And that's important because later we're going to be asking to find the formula for t of t so that we can move on to and use it to find the normal vector. So this is the unit tangent vector at a specific time 2 for this function. Okay, so defining the normal vector. The normal vector is a vector that is orthogonal or perpendicular to the tangent vector. Okay, they usually share the same point, and it might go in either this direction or in the other direction, depending on how the curve is moving. Okay, so the principal unit normal vector is the one pointing in the direction the curve is turning. So since the curve is turning to the right in this scenario, the principal unit normal vector is turning to the right. Okay, over here though, the principal unit normal vector would be turning to the left, since the curve is turning to the left. Excuse me. This unit normal vector is the derivative of t of t. So notice, not the derivative of this, because this would be the derivative of a constant and it would be a 0. So I'm looking for the derivative of big T of t in general divided by its magnitude. Okay, and I did a little proof here at the bottom. Sorry, this is going to keep happening. But is the derivative of the unit tangent vector really perpendicular to the tangent vector? So I started out with a definition that should look familiar from the dot product. Okay, so if I dot a vector with itself, any vector with itself, I should get the magnitude squared. And if you need to go back and look in chapter 11 for that, this would be a good time to pause and go verify that for yourself. But since I'm really interested in the derivative of the tangent vector, I'm going to take the derivative of both sides and see what happens. So I'm starting with something I know is already given information, and I'm moving to something that is the end goal that I'm looking for. So on the right side, if I take the derivative of this is a magnitude, so it's going to be a constant. This is going to be a scalar, and so the magnitude is a scalar, so when I take the derivative, I will get 0. On the left side, I'm just going to leave it for a second. But if you go back into your 12.2 notes, you should be able to find the dot product rule that says that, and this should have a dot here in the middle. I missed that, so a dot right here. The derivative of 2 vectors dotted together is the derivative of the first dotted with the second, plus the first dotted with the derivative of the second. And that's the part I missed. I should put a dot here for dot product. Okay, and it has to be the dot product because the derivative of a vector is another vector. So I couldn't multiply a vector times some kind of, a scalar wouldn't come out of here. So it needed to be a dot product of two vectors. Okay, since these are the same thing, because t and t are the same vector, I can write this also as 2 times t dotted with the derivative of the tangent vector. If I divide 2 to the other side, we get what we were looking for. That if I dot the tangent vector with its derivative, I get 0. And that dot product, if I get that the dot product of two vectors is 0, then I know that the two vectors are perpendicular. So just a little proof here of why the normal vector, okay, would be perpendicular to the tangent vector. Okay, so let's see an example of how we do this. All right, example 2, I'm asking you to find both the unit tangent vector at t equals 2 and the unit normal vector at t equals 2. So in the first part, I'm looking for the unit tangent vector. I have r prime of t first, okay, and then I take the magnitude of this in general. I didn't have to take the magnitude in general. I could have plugged in 2 and then taken the magnitude of that specific vector. However, in order to find the unit normal vector, I need to make a generic equation for t of t. If I had just made t of 2, I would not have enough information to move on to the next step. I have to make this equation in order to move on to the unit normal vector. Okay, so I have to do this anyway. That is the most important thing I want you to get out of this lesson, is that to find the unit normal vector, what we're looking for in part B, you have to have a formula for the unit tangent vector in general. And that's what we found here. And then I plugged in 2, okay, and I got 2/3, -2/3, 1/3. So now, to find the unit normal vector, I have to find the derivative of this function, the tangent vector up here, and I went ahead and I changed it into a function times a vector, which is part of our product rule. You could also split it up and do the quotient rule. It's kind of a preference, but I went ahead and I moved the function out here and then did a product rule. And you can check 12.2 for this rule as well, a function times a vector, taking the derivative of both. So I had to put it on 2 lines because I kind of ran out of room. But I have the derivative of the first part, the function, times the original vector, plus the original function times the derivative of the vector written here. Okay, so that is the product rule. Now, I do not, since I am just looking for the unit normal vector at t equals 2, I do not need to take the magnitude of this in general. Okay, I don't need to move on past this. There's nothing more than the unit normal vector that I need. So I'm going to go ahead and plug in t prime of 2. That way, when I evaluate the magnitude, I'm not taking the magnitude of this really long and gross function. So when I plug in 2, I'm getting this for the first part of my equation, this for the second part of my equation. Okay, I put those two together. Okay, I add them together, getting common denominator, and I get -4/27, -5/27, -2/27. Okay, so that is what's going to go in the numerator of my normal vector at 2. I need to take the magnitude of this, which I have factored out a little bit so that it will be nice and pretty. Okay, you don't have to, but again, it might be nice to simplify some of that away. So here I have, what this was here is the tangent, the derivative of the tangent vector evaluated at 2, and then I divided by this length, which is really like multiplying by the reciprocal, which is right here. And that multiplying by the reciprocal allowed me to divide this 9 and this 27 into a 3√5 in the denominator for everybody. Okay, and that is the normal vector evaluated at 2. So the other thing we should know, that's in the notes, is that what we did last class, if the function is parameterized by arc length, then it simplifies our procedures for computing the unit tangent and the unit normal vector. since, and this is because the magnitude of the derivative of the function, if, only if, it is parameterized in terms of arc length, is 1. And that simplifies our unit tangent vector to just be r prime of s. So this is the derivative of r with respect to s. And then taking the derivative of that to get the normal vector, I'm getting the second derivative with respect to s in the numerator divided by the magnitude of that vector in the denominator. Again, you should not write down these formulas unless you know that we are going to be working with r in terms of arc length. This is not a universal truth. Unless you have already gone and re-parameterized a function by arc length, then you may use these formulas. Otherwise, you need to do the formulas we were talking about above. Okay? All right. So I'm going to pause here, and I'm going to pull out 2 examples from 12.3 and talk about why this is true. Okay, so I pulled out 2 examples from the 12.3 notes to kind of talk about why the magnitude of the magnitude of the vector function when it is the derivative. Gosh, this is too many words. Okay, and what I want you to notice here is that if the function is parameterized in terms of the arc length s, when I take the derivative, I will get some kind of vector, because the derivative of a vector is a vector. But when I take the magnitude of the derivative of the function, only when it's parameterized in terms of arc length. This doesn't happen if it has t here. Okay, so but if it is parameterized in terms of arc length, I end up getting a magnitude of 1. So here I use example 5, which is the example we did with a line. So here I've written the equation of the line parameterized in terms of arc length. I took the derivative with respect to arc length, and I got this vector. When I took the magnitude, I got 1. Okay, and this is simple because it's a line, but it also works with functions. So for example 4, and you could go back and do example 3, it was just a little bit longer. Here is the vector function parameterized in terms of arc length. So after we were done subbing back in s over 5 instead of t. When I take the derivative with respect to the arc length, okay, don't forget chain rule, I get 3/5 cosine of s over 5, 4/5, and -3 sine of s over 5. If I take the magnitude of that vector, I get square root of 9 over 25 cosine squared s over 5, plus 16 over 25, plus 9 over 25 sine squared of s over 5. This sine squared and this cosine squared added together will be 1, so I'm getting 9 over 25 times 1 plus 16 over 25, and that is 25 over 25, and we get 1. Okay, so with our examples that we used from 12.3, you can start to see the trend that the magnitude of the derivative of the vector, if and only if it is parameterized in terms of arc length, will be equal to 1. And that's what makes those tangent and normal vectors so easy to find if our function is parameterized in terms of arc length. That is not likely going to be the case, but in case it is, our formulas get a lot easier. Okay, back to the notes for the last possible thing. So there's only one example here at the end because it takes a very long time. So this is where, once I explain what's going to happen here, or what the third vector means, I want you to take your time, stop the video, and go ahead and walk through this example by yourself. Okay, and then I will go through, because I'm only going to explain it very rushed, and you should try it with your partners or the people around you to make sure that you can do this. I would only ask you to do this type of question on a test one time, but I need you to be able to do it in order to be able to put all of the pieces together. So our last vector is called a binormal vector. It is perpendicular or orthogonal to both the unit tangent and the unit normal. And it's perpendicular to both, or orthogonal to both, because we create it by making the cross product of the unit tangent and the unit normal. And the binormal ends up being a unit vector as well. So not only is it orthogonal to the tangent vector, it is also orthogonal to the normal vector. Okay. It also allows us, now that we have 3 different vectors, we are going to define 2 different planes. The plane that contains the tangent vector and the normal vector, we call it the osculating plane. In order to write the osculating plane, remember, to write any plane actually, we need a vector that is orthogonal to this plane. So if this plane contains the tangent vector and the normal vector, the natural choice to write the equation of this plane would be to use the binormal vector, because it is perpendicular to both the tangent and the normal vectors. Additionally, we have the normal plane, which contains the normal and the binormal vector. To write the equation of the normal plane, I need a vector that is orthogonal to both the normal vector and the binormal vector. And the natural choice would be the tangent vector, because it is already orthogonal to the normal vector and already orthogonal to the binormal vector by definition. Okay, so by writing all 3 of these vectors, we are also finding some equations, for planes, because what we need to write the equation of a plane is an orthogonal vector, in this case the binormal vector, in this case the tangent vector, and a point. And usually the point will be given in the problem. So to wrap it all together, to practice making each of these vectors, I'm giving you a function here, e to the t sine t, e to the t cosine t. And I've given you the point 1, 0, 1. Now, that point is not good enough for us to plug in here because none of those values are t. So in order to find that, I need to take a look at each component. What value would make e to the t equal to 1? Well, 0. Would that value also work for the other ones? If I plug in t equals 0 into sine, I get 0, which is appropriate. If I plug in 0 into cosine t, I get 1. And if I plug it into this coefficient, e to the t, I also get 1, which is appropriate. So I know that my time is t equals 0. This will be the time that I'm going to plug in throughout my problem. Okay, so I'd like you to pause here, and with your table, okay, or with your friends, go ahead and practice finding the tangent vector, the normal vector, and the binormal vector. Okay, before you leave, the one piece of advice that I have is that in order to find the normal vector, you will need the general equation of the tangent vector. So you will need to find a formula for r prime of t divided by the magnitude of r prime of t without plugging in t equals 0. You will need that, you can see here at some point, okay, you need it to describe the vector. And I will actually need it because nobody, for the binormal vector, nobody wants to take the cross product of things with equations. If the binormal vector is going to be evaluated at t equals 0, find t of 0, n of 0, and then cross them to find the binormal vector. Okay, do not do a cross product of formulas in general. That sounds like a horrible idea. Okay, so pause here to find the tangent vector and the normal vector and the binormal vector. Okay, if you're coming back, we're going to walk through this really quickly, okay, just to show you what I've done. So first, in order to find the tangent vector, and look, also I would like to find the normal and osculating planes at the end, but I have to find all 3 vectors first to find those things. So to find the unit tangent vector, I found r prime of t. I had to do some product rule here in the middle, which was fine. But I went ahead and I took one extra step to factor out e to the t in each of these steps. I could have also factored it all the way out, as long as I don't forget it in my magnitude. That's a big issue sometimes. In order to find the tangent vector at t equals 0, I went ahead and I plugged in 0 into my vector here, and I got 1, 1, 1, which makes sense because I would get e to the t in all of them, and at least a cosine. And 0 makes sine 0. Then the magnitude of that is root 3, so my unit tangent vector is 1 over root 3, 1 over root 3, 1 over root 3. Okay, good. However, if I took the derivative of that right now, I would get that the derivative was 0, and that is not going to lead me to my normal vector. So I need to also, after I found r prime of t in general, I need to take the magnitude of this vector so I can make a formula for the tangent vector. So I take the magnitude here, and this looks pretty ugly. I want you to, don't forget that you have to FOIL these things. okay? But luckily, once you've FOILed, okay, and here's the e to the t from the first component, here's the e to the 2t that I factored out of both of these components, but I get a sine squared plus cosine squared, another sine squared plus cosine squared, and the two middle terms, cancel, and they actually cancel because they do equal 0. So I get e to the t plus e to the t times 2, sine plus cosine plus sine plus cosine squared. So I get 2 here. So really that's 3 e to the 2t's, which I can then take the square root of e to the t square root of 3. I factor that out because in order to make the unit tangent vector, I need to take r prime of t, which is here, and divide it by this magnitude. And if I do that, and by factoring out the e to the t, I can divide it out of every single term. So I get the formula for the unit tangent vector is 1 over root 3 sine plus cosine over root 3 cosine minus sine over root 3. Okay, that is the tangent vector. And to find the normal vector, we are going to take the derivative of this. So the derivative, once I've simplified, becomes a little bit easier. Okay, so I get 0. Notice I didn't do the quotient rule because this is just a constant I'm going to put on the side. Okay, so I've got cosine t minus sine t, 1 over root 3, negative sine t, negative cosine t. Okay, since I am only looking for n of 0, and in order to find b of 0, I do not have to have a generic formula for n of t. I can go ahead and plug in 0 right now. I do not need a generic formula for the normal vector in order to find the binormal vector. So I can go ahead and plug in 0 and it will be fine. So when I plug in 0, I've got 0, 1/3, negative 1/3. When I take the magnitude of that vector, I get 2/3. Okay, and again, when I divide t prime of 0 by this magnitude, I'm really multiplying by the reciprocal. And I like that because it allows me to divide out the square root of 3's. So I have to do 1 over root 2, negative 1 over root 2, and I get 0 still in the front. Okay, and I liked simplifying here because now I need to take the cross product. So I have to go back up and take t of 0, which was here, and take n of 0, which was here, and take their cross product. So I would like that cross product, since we all know how easy it is to mess up the cross product, I would like to be as simple as possible, which is why I made the active choice to simplify n of 0 before I plugged it in. So this is t of 0, this is n of 0, and I'm doing my cross product. Don't forget to subtract the terms in the middle and to do minus j. And you should get negative 2 over root 6, 1 over root 6, 1 over root 6. So the final step is to write, now that I have all three vectors, I can write the equation of planes. To write the equation of the normal plane, I'm using the point 1, 0, 1, and use the tangent vector at t equals 0 because it's orthogonal to the binormal and the normal. Okay, and the equation of a plane, I'm just putting the direction numbers here, putting the point here, and setting it equal to 0. And I'm done. To write the equation of the osculating plane, I use the same point, but I use the binormal vector because it's orthogonal to the binormal, I should use the binormal vector because it's orthogonal to the tangent and the normal. That's what that should say. Sorry, guys. So it's tangent to so it's orthogonal to the tangent and the normal. I should use the binormal vector here, though. So here are my binormal components. Here's the same exact point, set it equal to 0, and we are done. I know that's a really difficult and tedious problem, but the vast majority of it is actually just algebra. So I just want you to make sure you're getting familiar with making your algebra as simple as possible to support your multivariable calculus knowledge. Because if we had not simplified, this cross product would have been kind of ugly for us. So using our algebra to make our multivariable calculus more simple is our goal. Okay, but that is the 12.4 notes. Hopefully you get some practice, and don't forget to practice for the quiz on 12.1 through 12.3 next time.